Hello everyone, hope all are fine. So today we will be discussing about the frictional losses in pre-stressed concrete. So now I will be discussing about the frictional losses in pre-stressed concrete. So the friction is generated at the interface of the concrete and steel during the stretching of a curved tendons in post-tension member. So, when the cable is pressed, the friction between the sides of the duct and the cable does not permit full tension to be transmitted. So, because of this friction, the full tension transmission between the ducts are not happening properly. Therefore, at a point away from the jacking end, the pre-stress is very less. At the jacking end, the friction is very more. Because of that, the pre-stress cannot transfer till the end of the jacking end. That's why the friction in jacking anchoring system is generally very small. More serious frictional losses occur between the tendons and the surrounding materials. So if I talk about the frictional loss in post-tensioning member, the loss due to friction does not occur in pre-tension member because there is no concreting during the stretching of the tendons. That is, in case of pre-tensioning, the tension members, that is steel, is first stressed. It is first tension, and then the concrete is poured. That is, the concrete is not hardened at the time of tensioning of the tendons. That's why there is no frictional losses in pre-tensioning members. So friction is generally generated due to the curvature of the tendon and the vertical component of the pre-stressed force. That is, we can see in the image that due to the curved surface of the post tension members, we can see the friction is generally generated, and also due to the vertical component of the pre-stressing force. That is, when the pre-stressed force is put at some angle, then there is a vertical component of that force. It generates frictional loss. So if I talk how the frictional loss happens, frictional loss is due to two main effects. That is, one is the length effect and other one is curvature effect. So if I talk about the length effect, if the profile of the cable is linear, the loss will be due to the straightening or stretching of the cable. So friction due to the length effect depends only on three main things. That is the length, stress in the tendon, that is cable, and the coefficient of friction between the contact materials. So these are the three main parameters for length effect. If I talk about the curvature effect, if the profile is curved, there will be loss in stress due to friction between the tendon and the duct or between the tendon themselves. So curvature effect is caused by friction due to design curvature of the cable. So if there is a curves, if there are curves provided or by mistake and the curves are provided, then there is a loss of friction that is generated in the cables. So we can see in this image how the length and the curvature effects work. So ideally, the pre-tension, the cables or tendons should be in middle of the duct. But in reality, it is not at all possible. And we can see in this image, see here, that reality image, that the tension, the cables are coming down, which means that they are not straight and sometimes there will be curved in the duct. So this causes wobble effect and the curvature effect. Wobble effect is nothing but length effects. So in this way, the length effect and curvature effect come into the picture. So if I talk about the total frictional loss in the member, the post-tension member, it is given by Fx equal to Fe e power minus mu theta plus Ks, where Ks is the component for curvature effect and mu theta is the component for length effect. So now we will be solving a problem on frictional loss. So this is the question. A post tension beam 100 by 300 spanning over 10 meter is pressed by successive tensioning and anchoring of three cables A, B and C respectively as shown in the figure. Each cable has cross-sectional area of 200 square and has initial stress of 1200 MPa. If the cable or tension from one end and we need to estimate the percentage loss in each cable due to friction at the anchored end. we should assume mu as 0.35 and k as 0.0015 per meter. So we can see in the image there are three cables, cable A, B and C. And the cable A is 50 above the centroid at one end and is parabolic in nature. While the cable B is at the centroid, but it is also parabolic in nature. In case of cable C, it is a straight line with an eccentricity of 50 So pre-stressing force, as we know that it can be found out by multiplying the pre-stressing stress into the area. So we get the pre-stressing force as 240 kilonewton. To know the value of sigma L, the equation for the parabolic profile is required. So to know the slope at one end, we need this equation, differential equation, that is dy by dx equal to 4ym by L square of L minus 2x, where ym is the displacement of the CGS, that is centroidal axis, at the center of the beam from the ends, and L is the length of the beam, x is the distance from the stretching end, and y is the displacement of CGS at at the distance x from the ends. So an expression of sigma x can be derived from the change in slope of the profile. The slope of the profile is given by the equation, the same equation, dy by dx equal to 4ym by L square of L minus 2x. So at x equal to 0, the slope dy by dx is given by 4ym by L. We all know that at x equal to 0, 2x will become 0 and L is constant. That's why we get the equation 4ym by L. The change in slope sigma x is proportional to x. The expression of sigma x can be written in terms of x as sigma x equal to theta x, where theta equal to 8ym by L square. The variation is shown in the following sketch. So this is the variation of sigma with respect to L, which is given in the diagram. So the total subtended angle over the length is given by length L is given by 8ym by L. The pre-stressing force Px at a distance x is given by the equation Px equal to P naught e power minus mu alpha plus Kx. So we can rewrite the equation mu alpha plus Kx as eta x. So by substituting we can get the force as P naught e power minus eta x. So for cable A, Ym is 0.1 meter. In case of cable B, Ym is 0.5 meter, and in C it is 0 meter. For all the cables, L is 10 meters. So by substituting in the equation, substituting the value of Ym and L in the equation, we get eta x as 0.0043 x for the cable A, 0.0029 for cable B, and 0.0015 x for cable C. The maximum loss for all the cables is at x equal to L equal to 10 meters. That is the anchorage end, anchored end. So e power minus eta x is given is 0.958 for cable A, 0.97 for 71 for cable B, and 0.985 for cable C. So the percentage loss due to the friction is given by equation 1 minus e power minus eta L into 100%, that is percentage. So we get 4.2% in cable E, 2.9% in cable B, and 1.5% in cable C. So this is how we solve the problem for frictional losses. Now the question is how to reduce the frictional loss. So frictional loss can be reduced by adopting the following measures. The first one is cable should pass through the metal tubes properly and there should not be any gaps. The bend should be through as small as angle as possible. So the bend should not be more the angle should be very less. The radius of curvature for the bend should be very large. If the radius of curvature is very large, then it will become the curve will be very less. So the frictional loss automatically reduces. Pre-stressing the wire from both the ends. If the pre-stress is applied only from the one end, then at the end of pre-stressing force, the frictional loss will be higher, and the pre-stress cannot reach at the other end. That's why pre-stressing force should be provided on the both the ends. Over tensioning of the wires. So we can reduce the frictional losses by these five methods. So that's it from our side. Thank you.